And sometimes it gets really slow jumping between slide transitions here. So today we're talking about Wi-Fi, sort of an intro to Wi-Fi, what it is, how it works. We find getting out there and talking to people, even people that have been installing Wi-Fi for years, that there's a lot of myths and misconceptions about Wi-Fi, how it works. So hopefully today we'll clarify a few of those for you. So we'll start off with just a sort of a brief introduction of who we are here at Zyxel, in case this is one of our first webinars you've attended. So Zyxel, we've been making computer networking equipment for 30 years now. We were founded back in 1989. We have been doing Wi-Fi products since back before 802.11 had any letters attacked on the end. So back before 802.11b, back before 802.11a, there was just 802.11, and we were making products using those chipsets. Also, for the longest time, we had our own chipset development company known as Zydas. Have a number of really interesting patents out there. They were eventually sold to Atheros, who was then sold to Qualcomm. So today, just about any piece of Wi-Fi equipment out there that you are using is using some of the patents that Zyxel created back in the day. We've got 100 million devices out in the field, 150 different global markets served. R&D is done primarily in Taiwan, but we also have R&D in Santa Clara, California, and in Germany. So onwards to today's presentation, Wireless 101. Start with some of the basics here of Wi-Fi. So there's a couple names or acronyms you'll see them thrown around a bit when it comes to Wi-Fi. So these are all the main players in the space. There's the IEEE. So IEEE creates and sets the standards. So whether we're talking 802.11a, 802.11ax, 802.11n, or some of the other complementary 802.11 such as I, R, K, and V, those are all originally created by the IEEE group. It's an industry group that gets together and moves quite slowly at times, but tries to hash out and create the standards that everyone follows. So the Wi-Fi Alliance is a separate industry group primarily made up of the manufacturers and some of the chipset vendors. And the idea behind the Wi-Fi Alliance is to make sure everything plays nice with each other. So their primary focus is on compatibility between devices. They're also sort of focused on messaging to end users. They're the ones behind, for instance, renaming 802.11ax as Wi-Fi 6 and retroactively changing 11ac to Wi-Fi 5, etc. So generally, IEEE standard comes out first, and then down the road, the Wi-Fi Alliance will come out with their own testing criteria for interoperability that then has to be passed if you want to put the Wi-Fi certified logo on your device. And then there's the FCC, who here in North America is probably the big dog when it comes to setting rules as far as channel usage, power output, behavior, things like that. So that's the federal government that sets those rules and enforces those rules. If you go up to Canada, there's Industry Canada. Other countries have their own, although most countries, for the most part, follow the FCC rules with just a few minor tweaks. So let's talk about radio waves. So Wi-Fi is using, radio waves to send data. So instead of using an Ethernet cable, you are using a radio. It works very similar to walkie-talkies that you may have played with as a kid. Basically, one device at a time is allowed to transmit, and every device on the network takes turns transmitting. So just some basic stuff as a general rule: as frequency goes up, more data can be encoded on it. Though as frequency goes up, also the lower the range. Basically, the less penetration ability those signals have. So for those of you that are older, you might remember back in the days, good old 900 megahertz cordless phones. Those things were great, right? You could use one of those. You could walk out your house, walk a block away, and you'd still be able to hear your person on the other end and have a reasonable, good phone conversation. As time has gone on, cordless phones have moved to the 2.4 gigahertz spectrum and then up to the 5 gigahertz spectrum. So why? Why would they move to those? Because as I'm sure you've noticed, as that technology has progressed, the range has gotten less and less. So from 900, you used to be able to go a block down the road and talk. With 2.4, maybe you could go out to your front yard or the far corners of your backyard. And with 5 gigahertz phones, you're lucky to get any sort of reasonable call quality outside. So there were 2 reasons that drove that up. One was just spectrum availability. There's more spectrum available, so you're able to have more devices without them interfering with each other as you go up in frequency here in North America. The other benefit is, again, also you can put more data on there. So the quality of the call went up because you were able to use more data to encode the voice. So 2.4 is a much more crisp conversation with the trade-off of being less range than a 900 megahertz device, for instance. When we're talking about radio frequencies as a general rule require a license to operate. So you'll often see, spectrum bidding wars where companies like AT&T, Verizon, or Google will spend huge amounts of money buying up chunks of spectrum. So the FCC has allocated certain small bits of the spectrum that are available without a license. So that's the 900 megahertz frequencies that we were used to on our old cordless phones, 2.4 and 5 gigahertz. These are the 3 most common. There's a few others out there. For instance, 3.5 can kind of sort of be used without licenses. Some other chunks of spectrum have been set aside for governments, police, fire departments, things like that. So when we're talking about power, a lot of people talk in the terms of milliwatts. So they say, I've got a 200 milliwatt or a 500 milliwatt radio. Although generally when you're looking at spec sheets, you won't be seeing milliwatts. You'll be seeing power measured in dBm. The reason we use dBm is that dBm, you can add the gain caused by your antenna to the gain or the output power of the chip itself and do easy math to get to where your total output power is. It also is a better way of handling range. We'll get into it later, but basically range sort of drops off. This is kind of simplified, but it's an inverse square. So, as you increase the power, you don't see the same amount of range. So, for instance, every 3 dBm of power doubles your output power. So 20 dBm is 100 milliwatts, 23 dBm is 200 milliwatts, 26 dBm would be 400 milliwatts. But when you go from 20 to 23, you're not going to double the range because of how the power output actually drops off and is absorbed going through clear space. Another thing which people tend to ignore is signal-to-noise ratio. This is probably the most important thing out there, though, when we're talking about the Wi-Fi connection quality and the amount of data that you can send. So signal-to-noise ratio is the signal that you want to hear versus the background interference or other signals that you don't want to hear. So the ratio between those two tells you how good your connection quality is. So because of that, another really important thing which people tend to overlook is the receive sensitivity on the RF device itself. So generally, the better the receive sensitivity, the better it's able to handle signals in a poor environment where you've got poor signal-to-noise ratio. Another common term you'll come across is attenuation. So that's a measurement of the signal degradation after it comes out of the chipset itself. So primarily, we're focused on attenuation caused by path loss. So how much of that signal just gets absorbed in the air itself or dissipates in the air itself. How much of that signal degrades due to passing through materials such as walls, office furniture, human bodies. Generally, the thicker or more dense an object is, the more attenuation it's going to have. But if you're doing outdoor links and you're doing long distance point to point, then you have to pay attention to attenuation caused by connectors, cable loss, things like that as well. So up there on the top of the screen, that is the formula you use to calculate basically your distance that you can achieve when sending in a clear open environment with no other RF noise. So as you can see, it's using the logarithmic scales here of transmit power versus distance and frequency being used. So it's complicated. Generally, most people ignore this, but if you're doing outdoor links, you probably care about this. If you're doing outdoor point-to-point, there are a number of different calculators available for free and more advanced ones available for pay online, where you can put in the distance, height, things like that, and it'll help tell you what sort of range you might be able to achieve. Some other common causes of loss or attenuation here, you'll see a clear window, typical glass window, will add an additional 3 dB of loss on top of the free space loss. A tinted window, particularly one that uses some sort of metallic coating to help keep out infrared or UV, that can cause up to an 8 dB loss. A medium wall can have a 10 dB loss. A heavy wall, so like a typical cinder block, 15 to 20 dB. Thicker walls, such as solid brick, 12 inches or more deeper, can cause up to a 25 dB loss. So again, if you're looking at an access point, or more importantly, if you're looking at a client device such as an iPhone may only have 30 milliwatts of output power, or somewhere in the 10 to 16 dB output power. So that signal is not going to be able to get through the wall necessarily. Which comes into another really important thing here, which is when we're talking about Wi-Fi range. Generally, there is a huge disparity in power between your access point and your client device. So most business access points are going to be at least a 500 milliwatt output power. A lot of them are up to 1 watt or more of output power. But your mobile device can legitimately be anywhere from 8 to 25 milliwatts total output power. So while the signal from the access point can reach that device, the signal back from the client device won't be able to reach back to the access point, or the signal can get there, but the signal to noise ratio is so poor that you can't really send any data. So we get a lot of this where people will pull up their phone and their phone will show that you've got a nice strong Wi-Fi signal, but the connection quality is really poor. And this is often the cause of that, is this disparity between the output power of the access point. So your client device, your phone, your tablet, your laptop sees a nice, strong, clear signal. Unfortunately, it can't get the signal back to the access point. So James just sent in a question saying that a concrete cinder block wall degrades the signal more than a solid concrete wall because of the reflection within the core of the wall, air pockets. Is that correct? So this is going back to the previous slide. So the answer to that is there's a lot that goes into it. So these are just general rules of thumb. There's a lot of cinder block walls which don't have a lot of solid feeling, and they're generally only in the neighborhood of, I think, 8 inches. So if you compare like an 8-inch cinder block wall, the signal can get through pretty well, although you start adding rebar in there. Rebar causes all sorts of nasty stuff to happen with the signal. So yeah, I mean, those are just sort of, brief summaries, but what's in the wall, what's going on in that wall makes a huge difference. Another really nasty one for walls, which is really common here in Southern California, is stucco. So with stucco, you've got basically a wood base, it's hollow, but then you've got a layer of what's essentially chicken wire wrapped around that, and then concrete smeared on top of it. And that chicken wire kind of acts as a Faraday cage in often cases, absorbing the signal and making a huge block as far as penetration goes. So there's a lot of things that go into how much attenuation you're going to get with those walls as far as the materials go. General rule of thumb, though, is the thicker the wall, the more attenuation you're going to get. I just know from practical purposes out in the field, we have a lot more issues with older concrete buildings, or not concrete, older cinder block-based buildings where the walls are extra thick versus some of the newer stuff where you've just got a cinder block with filling. I hope that helps. Back to today's slide. So one thing to keep in mind here is just that signal disparity. You don't necessarily want to reduce the output power of your access points. That's something we see often suggested, is that you reduce the output power of the access points to match the output power of the client devices. because when you're doing that, you're lowering the signal-to-noise ratio both ways. And generally, you're more concerned with downstream bandwidth. Generally, your client devices are downloading or streaming video from the internet. They're not doing a lot of uploading. So you want that higher signal-to-noise ratio on the client device so they can get the maximum download speeds they can achieve. And in many cases, that will reduce the amount of airtime they're using. So here's an example here of RF behavior. So RF doesn't necessarily travel in a straight line. It can penetrate certain objects, which causes attenuation through diffraction. It can reflect off of devices. It can cause scattering. So these are all sorts of things that can cause issues in an environment, because as these signals bounce around, whoops, that's not the slide I wanted. If these signals bounce around, they can cause interference with themselves, right? So a signal bouncing off of one thing and coming at your other side may get there faster than the same signal that's bouncing off of 2 or 3 other objects before they're getting there, or bouncing off of the desk versus bouncing off of the ceiling. So those can cause issues. So we run into this a lot with factory floors and warehouses where you've got a lot of metal objects and a lot of surfaces that can cause a lot of bouncing and scattering and things like that. The other thing here to show is when it comes to traditional Wi-Fi, as I mentioned earlier, only one device is able to broadcast at a time. If 2 or more devices broadcast at the same time on the same channel, they'll interfere with each other. So going back to, if you remember when you were a kid playing with the cheap walkie-talkies, when you had a group of your friends together and 2 or more tried to talk, you would just get squelching and interference and hard to make sense of it. It's the same for Wi-Fi. So the way Wi-Fi currently works is before a device transmits, it checks to see if anyone else is transmitting. If it sees that someone else is transmitting, it'll back off, and it goes through a little random number generator to determine how much time it's going to wait before trying to check to see if it can transmit again. If it doesn't see anybody else transmitting, then it will go ahead and try to transmit a frame. Problem you run into that often is you start adding more and more devices onto an access point, is that 2 devices may both check simultaneously, both will see no one else is transmitting, and then decide to transmit at the same time, causing a collision and causing the packets to be dropped and need to be retransmitted. So this works fine in low density deployments, but as soon as you start adding more and more client devices, this ends up being a problem. We also have a thing out here called the hidden node problem, and this is caused where you've got clients trying to transmit to the same access point. The clients are both able to see that access point, but each of those client devices is unable to see the other client device. So they won't be able to tell that the other device is transmitting, so both will transmit at the same time, and that will cause interference to the access point, causing packets to be dropped. So it's a very common problem you run into. As you start doing denser deployments where you've got a lot of access points, we start running into issues where there's not enough available spectrum. So you've got access points using the same channel to broadcast on, and so you start running into these hidden node problems between client devices on different access points. So I'll just start off here. Those pie charts you see on the right, those are not necessarily accurate numbers. They're just there for illustration purposes. So we get a lot of data rate versus throughput. These terms are often used interchangeably. There are multiple definitions of throughput out there. So for the way we tend to see it being used on listings and product specs, the data rate is going to be the max amount of data that is transmitted between 2 wireless radios on 2 different devices. You will also often see this called the phi rate or physical rate or the link rate. So this includes not only the data that is being sent from whatever device is connected to that radio, but also all of the additional data that is being transmitted having to do with the Wi-Fi protocols, to do with error checking and things like that. So throughput is we're talking about on here. Throughput is going to be the data you are trying to send from your web browser, or from your application out to the internet or out to the other side. So this causes a lot of confusion for people new to Wi-Fi. If you go to Amazon, you can pull up any wireless router, access point, or device and read the reviews, read the negative reviews, and you'll see a lot of people complaining that they're not able to achieve anywhere near the advertised rate. So the 802.11 spec and the industry standard is to advertise the data rate, where most people, when they're using speedtest.net or FTP transfer, they're testing what we're calling today throughput. So they're only testing the data they're sending. They're not including the additional data that the wireless device is using. So a good example or contrast here is Ethernet. So with Ethernet, there is very little difference between the data rate and throughput, since you're talking about a dedicated physical medium that is only there to transmit data. There's not a lot of overhead on top of what's going on between the data you want to send and the media you're trying to use. Whereas with Wi-Fi, you're operating in a space, 2.4 or 5 gigahertz, where there are lots and lots and lots of other devices that may be trying to use that. Your microwave, Bluetooth headsets, cordless mice and keyboards, game controllers, you know, all sorts of home automation devices. So because you're in that noisy environment and you're having to share, there's a ton of additional overhead that goes into the Wi-Fi protocols to make that data transfer be reliable and make sure it's coming through without any sort of errors, distortions, or degradation of that data. So because of that, there is a huge amount of Wi-Fi protocol overlap that goes on there. So generally we'll say at something that has a 300 megabit advertised data rate will probably only be able to achieve throughputs from the user perspective of around 120 to 130. That's what you're going to see is going to be pretty typical. If you go to something like Small Net Builder, where they do really detailed throughput testing, you'll see that that's generally the trend. Is generally you'll be lucky to get 50% of the data rate as throughput, with the other 50% being the protocol overheads, retransmissions, and things like that, that also eat up that data that needs to be transmitted between the actual wireless devices themselves. Then on top of that, you know, as we talked about before, wireless signal degrades really quickly. So maximum speeds are only going to be able to be achieved at short distances and in clean environments. Once you start adding distance, interference, other objects, other devices in that space, you start seeing more and more degradation. So if you want to see how fast you're connected, Windows and most devices will let you see the actual connected data rate on top of the throughput that you're able to achieve. I hope that makes some sense. So just in general, how do you increase speed? I'm going to take a look at this from a chipset or hardware vendor point of view. So the main ways that you're going to be able to increase speed is you can increase the QAM encoding. So for instance, 802.11n uses 64 QAM, 802.11ac uses 256, and the new 802.11ax products are using up to a 1024 QAM encoding. So as you increase your encoding, you have to increase the horsepower of the wireless devices themselves to be able to process that additional level of encoding. Also, as you increase encoding, I believe generally it tends to be a little bit more prone to error, so retransmits need to go up. The other thing you can do is increase spatial streams. So 1 by 1, 2 by 2, 3 by 3, and we'll talk a little bit more about that coming up slides here. The other way to increase speeds generally is to increase bandwidth. So 802.11g used 20 megahertz channels. 802.11n used 40 megahertz channels. 802.11 AC traditionally uses 80 megahertz channels, although some products can use 160 megahertz channels. So again, we'll talk a little bit more about each of these. So let's just go back to some of the basics here. When we're using 2.4 gigahertz, in the US, we've essentially got 60 megahertz of spectrum to use. And it gets confusing because when you pull up the GUI, you'll see 11 channels that are available in the US, 13 in some other countries. But each of those channels are only 5 megahertz in width. But the Wi-Fi channel we're using is 20 megahertz. So obviously, if you use one device on channel 1 and another device on channel 2, there's going to be overlap. So what we see is when using 20 megahertz channels in the 2.4 gigahertz spectrum, you've only got 3 non-overlapping channels that you can use. So as soon as you're in an environment where there's more than 3 access points or where there's more than 3 2.4 gigahertz devices, you're going to start getting interference. And to make it even more confusing, there's actually more overlap in that 20 megahertz if those devices are located really close to each other. So if you've got a access point on your desk and you've also got some other wireless, non-Wi-Fi 2.4 wireless devices on your desk, you'll be able to use non-overlapping channels, but you still may get interference because these channels on the long tail tend to interfere with each other on short range. We call those band edge issues. So something that happened towards the end of 802.11g is you started seeing vendors advertising turbo products. There were various different proprietary ways of doing this based on the chipset that used 40 megahertz channels. And with 802.11, 40 megahertz became a standard. But again, we've only got 60, essentially, megahertz of spectrum here in the US to play with. So obviously, if you're using 40 megahertz channels, you're going to get interference as soon as you add a second device on there. So take that into account as far as interference goes. 5 gigahertz has been where we've been trying to push people in the industry for a long time. And the reason for that is because you've got a lot more spectrum available. So if we go to 20 megahertz channels, I believe we've got 19 non-overlapping channels that in theory you can use. So one thing though I do want to point out here is you will notice the middle section has some orange and yellow area there highlighted as DFS channels, and a separate section specifically mentioned as being weather radar. So we need to talk about that a little bit. So DFS channels is a portion of the 5 gigahertz spectrum that is used by radar systems, both weather radar, airplane radar, military radar, things like that. So because we're sharing this spectrum, the FCC has put rules in place where you have to make sure, if you're using it for data communications for Wi-Fi, that you are not causing interference with these radar devices. So if you're using these near a military base, near an airport, you're going to run into a lot of potential problems. So the way DFS works is the device itself, specifically the AP, needs to check and make sure that channel isn't being used. So when the device first boots up, there is going to be a period of time of several minutes where that access point will not broadcast anything because it is monitoring the environment to make sure the channel it's using is not going to be used by a radar device. So that's one complaint you get is, well, I've rebooted the AP, now I can wait maybe 5 minutes before my access point starts broadcasting again, because it's checking to make sure that it is safe to use those channels. Another problem you run into in using those channels is some of the radar isn't going to be consistent. They may only, especially if you're near a military base, they may only power it up periodically. So what happens is if your access point is operating and it detects suddenly that there is radar-based usage of those channels, your access point has to stop using that channel for 30 minutes. So it's really hard if you're near one of those devices to be able to maintain a steady, stable connection. So it's a really big problem for those of you that are doing this types of activities. And then on top of all of that, getting this DFS certification, it requires a little bit extra horsepower in the hardware. but it also requires up to 6 months additional time versus normal FCC certification to get that certification. So in the consumer space, where people are trying to rush hardware out as soon as chipsets become available, is that a lot of consumer devices don't support DFS. So we go from having theoretically 19 non-overlapping channels. If you decide, you know what, I can't use DFS because maybe it's not going to be stable enough due to interference from weather radar or other forms of radar based on the location, or alternately, you're in a situation where people are bringing their own device, you will run into people who will bring their device and they won't be able to connect if you're using one of those DFS channels because their device doesn't support it. So now you're down to just 9 non-overlapping 20 megahertz channels. So as we talked about before, one of the ways we increase throughput with some of the newer standards is by increasing the channel width. So if we go up to 40 megahertz channels, now you've only got 4 non-overlapping, non-DFS channels that you can choose from before you start running into interference issues. And most of the current 802.11 AC devices out there are going to default to trying to use 80 megahertz channels. So now you're down to just 2 non-overlapping channels if you don't want to use those DFS channels. So really big issue if you're doing hospitality, where you really have to consider that. If you're doing office-based coverage where you're controlling the devices on the network, it may not be as big of an issue. And then as we saw here with Wave 211 AC and with 802.11 AX, they now support 160 megahertz channels. So to operate using those 160 megahertz channels, they have to overlap with DFS. So it's not really practical from an interference perspective. It's not really practical from a DFS situation in a lot of deployments. So just right there, if you're talking about maximizing speed, you know, a lot of the newer stuff that supports 160 megahertz will be advertising those speeds. But realistically, unless you're using this in a, you know, a single family dwelling, you're not going to be able to use those 60 megahertz channels due to interference caused by your neighbors. So now on to spatial streams. So we have what we call a multipath problem. We talked about before that as the signal radiates out, it can bounce off of things. So traditionally we've had this thing called multipath, which caused a problem, which is the signal would bounce off of multiple different objects, and you'd end up splitting that signal out into multiple streams, which would all end up on the receiver end of things coming in at slightly different delays because of the different length of distance that multipath caused. And this would cause interference issues. It would cause signals to combine, signals to cancel out with each other. So it used to be a really big problem. So somebody came along, and it might have been at least in part Zyxel, our old chipset vendor, and found ways to take what was previously a problem with multipath and turn it into a benefit. So one of those big benefits we got here is something called MIMO, multiple in, multiple out. So we really started to see this with 802.11n is where we first started seeing MIMO being advertised. And you would see a home router which would have 2 or 3 antennas stuck onto it. And the reason for this is to take advantage of multipath. And what you would do is you would actually send data, different amounts of data off of different antennas. So this is the example we sort of have here in this diagram here. One radio or one antenna is sending 150 megabits of data. It bounces off of object 1 there, desk, wall, whatever it is, and then gets to the client device. Antenna 2 will send a different, slightly offset stream of data, and it'll bounce off of a different device, and both will arrive essentially at the same time at the client device, but each of those we're going to call a spatial stream, and each spatial stream is capable of carrying different amounts of data. So that's one of the ways where we're increasing throughput speeds, is by increasing the number of spatial streams. So that's why a lot of your higher end access points will have a ton of antennas poking out and sticking out across them. So it increases overall throughput. The other thing you can do with spatial streams is something called MIMO, multi-user MIMO. So instead of using the spatial streams to send multiple streams of data to the same client device, instead what you can do is you can use this to send different streams of data to different individual client devices. So instead of sending 300 megabytes to one device, you'll send 150 megabits to one device and a separate 150 megabits to another device. So with 802.11ac, this can only be done downstream from the access point to the client device. With 802.11ax, you will get the ability for clients to be able to take advantage of MIMO to send data back to the access point. So the benefits of this are if you've got, you know, a 2x2 or 3x3 or 4x4 access point, but most of your client devices are 1 or 2x2, you would traditionally not be able to take advantage of your full speed. So by using MIMO, now you can transmit to multiple slower client devices at the same time, maximizing your airtime and overall throughput. So one of the things you're going to see when you look particularly at business devices, consumer devices tend to just sort of add all the speeds together, and they'll advertise the devices AC 1200, AC 1750, AC 5800, whatever. On the business side of things, traditionally what we tend to do is we tend to focus on the spatial streams. So you'll see a lot of the devices out there marketed as 2x2, 3x3, 4x4, etc. So the first number is the number of antennas that can be used to send different spatial streams. The second number is the number of antennas that can be used to receive different spatial streams. So basically each antenna is able to handle one spatial stream. And we do this on a per radio basis. So generally if you see something advertised as 2x2, that means you've got 2 spatial streams that you can use for each of your different radios. So you've generally got 2 radios in most modern access points. You will sometimes see a mix mash. For instance, on our NWA 1123 ACHD, the 5 gigahertz radio is 3x3, whereas the 2.4 gigahertz radio is only 2x2. So you'll see both of those listed, 3x3, 2x2, or 2x2, 3x3. Another thing you'll see, Cisco likes to do this, is they'll advertise a product as 4x4, there'll be a colon, and then the number 3. So they've got 4 antennas on there, but they're only actually able to use 3 of them at a time. So you've really only got 3 spatial streams. So the colon and then the number after that is the actual number of spatial streams you can use, where the first number is just talking about the potential number of antennas that can be used with those 3 streams. In a real world perspective, it doesn't really make a lot of difference. It used to be really popular in the early 802.11n days. You would see a lot of 2x2 devices with 3 antennas. But the benefit you get from having more antennas and you have spatial streams that you can choose from is really minimal. So to put that all together, here's a little chart showing you the different speeds you can achieve, data rates that you can achieve based on QAM encoding, the number of spatial streams, and the bandwidth that's available. So for instance there, if you go down to Spatial Streams 2, 64 QAM, 40 megahertz, you'll see the maximum speed is 300, which is our traditional 2x2 802.11n or 2.4 gigahertz radio speed. If you go to one spatial stream, 256 QAM, 80 megahertz channel, you'll see it's 433 is being the maximum data rate, which is your traditional 1x1 802.11 AC speed that you'll see claimed out there. So a common question we get is how many devices can we get on one access point? And oftentimes you'll see vendors out there pointing to a ridiculously huge number. They'll say, hey, we support 128, we support 256, we support 512. That's not really truthful. What they're looking at is they're basically saying our association database can support this many associated client devices. The real limit, though, of the number of client devices that you can get on an access point is going to be much, much lower than that, just based on the way 802.11 functions. So generally, the limit to the number of devices you can get on an access point has nothing to do with the access point itself. Most of modern access point hardware all have enough horsepower to be able to greatly exceed, in theory, the number of actual devices you can get. So any modern access point, whether it's cheap or expensive, is going to have essentially around the same amount, support the same amount of client devices in real world terms, because the limitation is the way 802.11 currently works. As I mentioned before, only one device can transmit at a time, and the client devices basically check to see before they transmit if anyone else is transmitting. If someone is, they back off a random amount of time, check again, and then transmit. So what happens is, as you add more and more devices onto the network, eventually you start running into devices both deciding to transmit at the same time, and you start getting interference from that. So realistically, how many client devices you can get on AP have to do with the type of device. Are they 1x1 devices? Are they 3x3? Signal strength, interference and obstructions, and just what sort of traffic they're using. You know, if you're doing something like just browsing the web, you can get a lot of devices on there and they have no issues. But if you've got a lot of people wanting to stream Netflix, where you've got a constant amount of data that needs to be transmitted one at a time to each device, you're quickly going to eat up that airtime, the available airtime for devices to be able to transmit. Or if you're doing something like voice, you're doing VoIP over Wi-Fi, it's not a bandwidth intensive thing, but it's sending out a bunch of small, steady packets that need to be able to be transmitted and received in order without any drops. So VoIP is really prone to interference, even though it's not using a lot of bandwidth. So that all plays into it. So this is sort of an example here of we're using the same access point, same basic assumptions, 20 megahertz channels, 5 gigahertz receive sensitivity. And we're looking at airtime utilization, what sort of speeds can you get? So if you're using a device that supports 3 spatial streams, on an access point that supports 3 spatial streams, you're going to be able to get 34 laptops on there, each transmitting at 3 megabits per second. If you go to tablets, which only support, say, a 2 spatial stream, you suddenly now can only get 21 devices on that same access point using the same amount of speed because they're not maximizing the airtime utilization. We're assuming in this case you're not using MIMO to fill the gaps. And then if we go down to, say, a smartphone, which only has 1 spatial stream support, it's only got the 1 antenna built into it, you're only going to be able to get 10 on that same access point with the same amount of data usage. And the same sort of thing, this is obviously a simplified way of talking about this, but obviously other things go in there. You know, probably the best thing you can do for airtime utilization is maximize your spatial streams and be as close to the access point as possible so you've got the fastest possible data rate. So you're minimizing the amount of airtime you need to transmit the same amount of data, right? So as data rate gets slower, it takes more and more airtime to be able to transmit the data because the data is being transmitted at a lower speed. So you can see here just what a dramatic difference it makes in the number of devices you can get on that access point and the overall throughput that you're able to achieve based on the type of devices that are connected. So another problem we run into out here, and I've talked about this a lot when dealing with airtime, is co-channel interference. We see this a lot out there, especially in dense deployments or when you're deploying in apartment buildings and condos, or when you're deploying in an office building where you've got a lot of smaller offices, so you're only able to control the access points in one office and you have no input over the nearby office spaces. So you'll run into issues where you add more access points, but your performance on the network actually goes down. Things like that. So that's something called co-channel interference. So, you know, we talked about this before, this really inefficient way that Wi-Fi determines whether or not they're able to transmit, co-channel interference issues, hidden node problems, things like that. So what that is basically is just interference between the multiple devices in this tough deployment. So traditionally, the way you've tried to get around co-channel interference issues, I think this is animated, yeah, is you might try to turn down the power on your access points. But as we talked about before, if you turn down the access point power, you're lowering your signal to noise ratio, so you're slowing the data rate that's available. So you oftentimes end up getting just as bad or worse results by turning down the power to avoid the interference between access points. Whoops, that didn't work like I thought it would. Oh well. Other issues that you would have here is obviously you do try to do careful channel planning where you plan out your channels so no two APs next to each other are using non-overlapping channels. But as we talked about, some of the issues you run into that is if you're using those wider channels, you've only got, you know, 1, 2, 3 channels that you can use before you get interference. And the access points have to be a surprising amount of distance from each other before they don't cause interference. To avoid co-channel interference, that interference from that other access point or other client device has to have a signal strength of less than, I think it's 79 dPm. So even a really weak signal causes co-channel interference. So the distance those access points realistically have to be kept from each other is a unrealistic amount of distance in a real-world environment. In open space, we're talking hundreds of meters between those access points to avoid co-channel interference. Obviously, where you've got walls and things like that, it's a little bit closer, but it's still a surprising amount of distance that those APs need to be kept from each other. Okay, I did have interference. I must have double-clicked it there. Okay. So traditionally, when we're talking about antennas, we have a fixed antenna pattern. Generally, access points are designed to be mounted onto a ceiling. So they have a round omnidirectional sort of antenna pattern. If you're doing point-to-point bridging, you generally use a much more focused directional antenna. So Zyxel and Ruckus use something called smart antenna. We're the only two vendors that have smart antenna devices. I'm specifically going to be talking about our smart antenna implementation. So basically, with smart antenna, you've got the access point has the ability to dynamically choose from hundreds or thousands of different antenna patterns. So in the case of our smart antenna, we look at where the client is, and we try to choose an antenna pattern that maximizes the coverage for that client, both for transmitting the data to them, but also on the receive side of things. The other thing we do is we take a look at other sources of interference that might be out there, whether it's other access points or industrial equipment, and we tailor that antenna pattern to not only maximize focus towards the client device, but also to take into account the RF noise to sort of ignore that RF interference. And it works, unlike beamforming, it even works with mobile devices where it's able to keep up and keep changing that antenna pattern based on where that client device moves to. So using smart antenna technology like this makes a dramatic difference when it comes to co-channel interference in the real world. So this is a test scenario we put together. In this case, it's a hotel environment, but it's just as applicable to a business office environment. So you can see here, we're using a bunch of access points. Each access point is serving a simulated 2x2 client devices, where there's going to be some co-channel interference between them. So you can see the ones that are circled there are going to be on the same channel, even though one's on a different floor than the other two, and the other ones are separated out with multiple access points in between. So in this test that we set up, we used Zyxel NWA1302 AC, which is our wall plate access point with smart antenna. And we used a Ubiquiti UAP AC, their wall mount. It doesn't have smart antenna. Although the results you're going to see here, we're using Ubiquiti for this test. These are going to apply to any non-smart antenna access point. So what we did is we first simulated it with one access point operating. And as you can see, both us and the Ubiquiti were able to achieve approximately 67% of the theoretical maximum throughput that was achieved. So in this case, with 2x2, 5 gigahertz, 11 AC client devices, the maximum throughput that you could expect to see in theory is 600 megabits per second. So both us and Ubiquiti were just above 400 megabits is what we achieved with 2 simulated clients on that access point. So no real benefit to smart antenna in that situation. So in round 2, what we did is we added a second access point. As you saw, we turned on that second one. It's a few rooms over. And then simulated the throughput you could achieve with 2 clients on each of those access points. So what you see is with smart antenna, we're able to actually achieve overall throughput greater than the maximum theoretical that you could get because those access points are essentially able to create, even though they're operating on the same channel, the smart antenna allows us to basically create a faux isolation, additional isolation between those access points. So what we see is with 2 access points operating, we were able to achieve a 785 megabits aggregated throughput. Where with Ubiquiti, we were only able to achieve 555 megabits aggregated throughput. You'll also notice that with the smart antenna, both access points have around the same amount of overall throughput, whereas with a non-smart antenna access point, you start seeing some disparity there, with one access point hogging up basically the available airtime to transmit. So the next test, we simulated 3 access points operating at the same time. And you see the overall channel efficiency has gone up. So in the previous slide, we were at 131% of the theoretical maximum. With 3 access points using smart antenna technology, we're able to get up to a total of 155% of the theoretical maximum because of the additional simulated isolation that smart antenna is able to achieve. And again, if you look at that top chart, that throughput was pretty fairly distributed amongst each of the access points that in theory should be interfering with each other. If you look at the non-smart antenna access point in red, you'll see again that there is not that sort of equal distribution. It's each access point fighting for itself. So you're going to end up over time with a really unstable environment as each access point takes turns basically being the airtime hog. You'll also see that with the non-smart antenna with 3 access points on the same channel, their efficiency actually went down. They went from 95% of the theoretical maximum down to 91% of the theoretical maximum. Well, with smart antenna, you were able to go up. So the takeaway from this is smart antenna makes a huge difference in these dense deployments. So whether it's an open air environment like a expo center or concert hall, or whether it's just a dense environment such as apartments or hotels or offices in a shared office building, smart antenna is going to make a huge difference to the overall experience of the end user connecting to those access points. So another challenge that we commonly run into here is, again, I was talking about before, these smoke detector type access points, these round, or in the case of, I think, some of our competition, square access points. They're designed to be mounted on the ceiling. So the antenna pattern is maximized to provide a sort of umbrella-shaped coverage pattern. So what we find, though, is a lot of times people will have taken these access points and mounted them on a wall instead of on the ceiling, or they've mounted them on the ceiling next to a wall where the wall is going to be blocking and absorbing a big chunk of that coverage area. So this is something to take into account when you're planning where you're deploying these, is if you're using a traditional access point, you really want to be mounting it on a ceiling above the clients and ideally in the most central location possible. Otherwise, you're just sending a bunch of the signal into the wall or into the ceiling and floor. So just some general mounting tips for you. You know, when you're using a traditional smoke detector type access point, you want to mount it on the ceiling. If you go to something using smart antenna, that gives you a lot more flexibility as far as mounting it on a wall. We also, as you guys probably know, offer a number of access points that have dual antenna configurations, a ceiling mount and a wall mount configuration that you can switch between based on where you do the installation. Another general guideline is you want to mount the access point generally as high as possible in the area because that allows you to avoid obstruction. So you can see in the photo there, we've got your traditional cube type environment. By mounting the AP up on the ceiling there, you allow the signal to easily go from the laptop or computer directly to the access point without having to propagate through people, cubicle walls, things like that. In some cases, it's not a good idea if you're doing a large warehouse or you're doing a large expo center. You want to keep it within reason, so you may need to lower the access points in those cases just to try to deal with co-channel interference issues because you don't want the access point picking up noise from the entire show floor. So we get this question a lot, which is, you know, should I mount the access point on the drop ceiling? Our experience in the real world is while you absolutely can, generally a drop ceiling has very little signal degradation. So we suggest in a lot of cases to actually mount above the drop ceiling. All of our access points that we sell are plenum rated, so they can be mounted up there even if it's rated plenum space. We have a number of customers that I can think of that actually just rest the access points above the drop ceiling on the drop ceiling itself rather than mounting them, which is fine. That way it's out of sight, out of mind type of thing. You don't have to worry about people smacking them, grabbing them, being distracted by the lights on them. The only thing to take in mind is when you're mounting them above the drop ceiling, you know, a lot of times up there's a lot of duct work, metal duct work. So that's not always good for connectivity. Lighting also can cause some issues with the signal. So it's a trade-off, but we've had a lot of our partners have a lot of luck just mounting them above the drop ceiling rather than on the drop ceiling itself. From a hotel situation, we talk a lot, or traditionally the way of doing it has been to use what we call an umbrella coverage. You mount the access point in the hallway, and you have one access point for every 4 rooms, or every 6 rooms, or every 8 rooms. That is going away as far as the industry trend is. The industry trend is using one access point per room or one access point for every other room. So the reasons for this are generally have to do with user experience and the fact that people are doing a lot more streaming and are a lot more demanding of the Wi-Fi environment. As we talked about before, client devices that people are bringing into a hotel room are generally very low power. So they oftentimes have issues getting the signal back out to that hallway mounted access point, especially with a lot of hotels have the plumbing and the fixtures in that wall that runs along the hallway. So those pipes and things like that cause all sorts of issues. And just wanting that client to have the maximum speed possible. So that's the new trend that we're seeing. We're also seeing the same trend taking place in large stadiums. So rather than mounting access points on the ceiling or along the walls and using directional antennas to try to minimize interference, what we're seeing is mounting access points under the seats with a lot more spread out to provide that localized coverage area to increase the overall throughput. So it'll be able to handle things like people live streaming while they're at the game or while they're at the concert, etc. In the hotel environment, you'll want to look for access points that the AP mounting can be locked to make it difficult for guests to steal access points, because guests will steal access points. So most of our mounting brackets have some sort of locking mechanism that a guest isn't going to be able to figure out on their own. The other thing to do is make sure your access points have the ability to turn off the LEDs. Nothing more annoying than trying to get to sleep while this seeming smoke detector in the room is flashing a bunch of green or amber lights as it's in use. So make sure the access point has the ability to turn off the external LEDs if being mounted in where a guest might be sleeping. As a general rule, in public areas, you want to plan how many access points you have based on the density of users, not the space to be covered. So if it's an environment where you expect to have a lot of guests online, you want to put in more access points. In those public areas, use load balancing and client steering to help prevent any access point or any one radio from being overloaded. And in general, you provide different areas with their own coverage. So the hotel lobby would have different access points serving it versus the next door cafe or restaurant versus the bar versus the swimming pool area. So in these dense environments, smart antenna makes a huge difference in guest satisfaction and the quality of connection. For schools, questions to ask is how many students are going to be in each room? Does each student have a Wi-Fi device? We're seeing more and more classrooms where each student has a Chromebook or tablet. So you'll have 30 or 40 people trying to get online at the same time. And then are they just browsing the web and uploading files, or is the teacher taking remote control of those tablets and streaming video to each individual tablet? We see this being done more and more. As a general rule, teacher and students should be on different networks. It can be the same hardware, but you need to have those VLANed off and isolated from each other. So you can put more restrictions on what the students are doing so they're not goofing off during class, or teachers will need much looser or less restrictions on what they're doing. Generally for class sizes of 20 students or larger, we suggest using 2 access points per classroom. Both our wireless LAN controllers and our Nebula Cloud Management both have a special load balancing algorithm that you can choose that's been designed just for smart classrooms. And then last slide here today is 802.11ax. It's kind of a confusing space. It's a new standard that's coming out. You've seen the Wi-Fi Alliance has decided to brand it Wi-Fi 6. You will see some other people branding it High Efficiency Wireless or HEW. So what is that? And what's going on? We see, if you look out there, you will see that it's not been ratified, yet you see vendors out there selling products that they claim are 802.11ax. So short versions of it, 802.11ax is bringing a ton of improvements to 802.11. They've essentially thrown out as much as possible of the old standards and have rebuilt it as much as possible based on the increased way that, the increased bandwidth utilization that we see going on with Wi-Fi versus when it was first created. It's designed to work on both the 2.4 and the 5 gigahertz radio. So unlike 11AC, where most of the benefits were restricted just to the 5 gigahertz radio, you will see these benefits applying to both the 2.4 and the 5 gigahertz radio. It's been designed to create some dramatic improvements in throughput in high density deployments. So you can get an actual up to 2 times throughput improvement at the same data rate with 802.11ac. So it's pretty huge as far as from a real world perspective, as far as the benefits people are going to see, even if the data rate doesn't look faster. So the way that we are doing some of these, achieving these things is going up to 1024 QAM, going up to OFDMA. This is a huge difference. So like we talked about before, one of the biggest problems with Wi-Fi and maximum users is the airtime and the way that hidden node and just the inefficient way we back off if we see that someone's already using the channel lead to inefficient use of airtime. So with OFDMA, the access point is now going to be able to coordinate and allocate specific bits of airtime to the individual clients. So instead of the client having to guess whether it's clear or not to transmit, the access point will say, okay, client number 1, you can transmit this many frames, go. Then it'll go, client 2, now's your turn, you go. So this makes a huge difference in these dense deployments, classrooms, expo centers, concert venues, things like that. It's going to make a big difference. You are seeing uplink MIMO. So before we talked about multi-user MIMO only worked transmitting data from the access point to the client device. So with Wi-Fi 6, you'll be able to have multiple client devices transmit data back to the access point at the same time. And you also have this thing called spatial frequency reuse, where we're able to assign client devices onto individual sub-channels, so multiple devices can work at the same time on the same overall frequency. So this is what's coming with 802.11ax. So anything you see out there today marketed as 802.11ax is not 802.11ax. This is back, I don't know if you guys remember 802.11. There was a lot of draft product out there, and everyone told you, hey, this draft product, it'll be software upgradable to the full standard. It wasn't. There was draft 2.0 products, and only some of those could be upgraded, so you ended up with a mishmash of pre-standard based equipment, and that's exactly what we're seeing right now with 802.11ax. Anything that's out there right now is missing big chunks of what's part of 802.11ax. And the chipsets themselves are not going to be software upgradable to the full feature set. The other problem you run into with 802.11ax is all of the hardware that's out there right now is designed for the access point or router. Client devices, even based on the draft spec, aren't expected to be available for another 18 months from today. So to achieve most of the benefits of 802.11ax, the client device also needs to support these new standards, and they won't be out there for another 18 months. So my advice is don't rush out and start putting in 802.11ax equipment yet. Wait a while until the chips that are out there are for sure going to be compatible with the final version. And even then, you're not really going to see any of the benefits until client devices start hitting the market. So you're still, again, looking into 2020 at the theoretical earliest before you'll actually be able to take advantage of an 802.11ax network. So the latest updates I have is the actual IEEE working group. The official standard coming out of that working group will not be actually voted on and approved until January 2020 at the earliest. Final approval won't be available until March 2020. So nothing can be guaranteed to be said to be 802.11ax compliant until that final standard is approved. Based on what we hear from Broadcom and Qualcomm, the two biggest chipset vendors out there, silicon that supports theoretically the full feature set won't be available until probably late Q3 or Q4 of this year. So you will see chips out there at the end of this year getting a little bit ahead of the final working group vote that should support everything in the working group draft end of this year. So I hope that helps. That concludes today's webinar. If there are any questions, go ahead and send them in via the Q&A box. I also wanted to draw your attention to an area where you can ask questions 24/7. We have a dedicated Zyxel forum just for our business products. You can find it by going to forum.zyxel.com. Our engineers and support team do check that board regularly and will weigh in on questions. So if you don't have time to call in to ask a question, or you don't necessarily need to reach out to our dedicated support team, you don't need an answer right away, this forum is a great way to get your questions answered, whether they're hardware, technology, or theoretical questions. So go ahead, let's see. I'll start going through some of the questions that have already been sent in. Tony is asking, can we get a copy of the presentation? We are making a recording of this presentation. Will be available in a couple days. If you reach out to your salesperson, we can provide you a copy of a PDF version of this presentation as well. Stuart is asking, Can you mention the differences between these APs that have antennas sticking out from them and those that do not? So the general answer is it doesn't normally make that much difference whether you've got the external versus internal antennas. Early in the days, you would use those external antennas and you would put in different types of antenna based on whether you were trying to do directional or based on the gain you were looking for. For the most part, internal versus external doesn't make that much difference. Today's internal antennas are a lot better than the old ones and provide generally just as good as coverage as the external ones do. And in some cases, internal actually is better simply because when we talk about using those multiple spatial streams, it's easier to optimize for fixed antennas that aren't moving around, where most of your external antennas, the user can bend them or twist them or point them different directions. And that sort of messes up some of the calculations that are done for those spatial streams. So as a general rule, most newer access points don't have external antennas at all. The reason to have them and the benefits they provided have kind of gone away. James is also asking about this again. The webinar has been recorded. It should be published on our website in a couple days. You can also reach out to your salesperson and get a PDF version of the slides. Jack is asking, do all Zyxel access points include smart antenna? And the answer to that is no. Smart antenna adds about $100 to the cost. So only certain models have it. So basically all of our access points are available in a smart antenna and non-smart antenna version. Smart antenna access points are NWA 1302 AC, and then our WAC 6303D-S, WAC 6502D-S, WAC 6503D-S, WAC 6552D-S, or also the NWA 5302D-S, I believe. So generally, if they end in -S, they're smart antenna, and then also the WAC or the NWA 1302-AC is also smart antenna. That information is also on the data sheets and things like that. Donald has a question here. When you are in an office or hospitality environment and have multiple access points and you're all broadcasting the same SSID, can a user drift from one area to another and switch access points without having to switch SSIDs? So that's a good question from Donald. A lot of people are confused by this. So yeah, you can have all of your access points using the same SSID. And traditionally with Wi-Fi, roaming is handled by the client device. So it is the individual client device that determines when to move from one access point to another. And the algorithm that they use varies between hardware vendors and chipset vendors. So some devices are much better at roaming than others. You'll often see in the term, or in the industry, a term called the iPhone problem, because iPhones have been pretty horrendous when it comes to roaming. They traditionally do not want to move from one access point to another. Will stay connected to that first access point even if the signal is really weak and they're standing right next to an access point with really good connectivity. I think the newer iPhones have solved it, but some of the older models, this was a huge problem with them. So there are a number of tricks that have been implemented on the access point to help try to force the device to roam. Most of our access points have the ability to automatically kick a client off if we see that the signal strength is too low. So that's one way around it, and then we'll block them from reassociating for a few seconds to try to force them to reconnect to a new, closer access point. The industry itself has come out with some standards, 802.11k, 802.11v, 802.11r, which help with roaming and allow the client or the access point to sort of coordinate with the client device to help them roam and help them know that they should roam, but not all client devices support that. And then like we talked about, 802.11ax, I believe, has some additional features that are designed to give the access points more control to force the client devices to roam. James is asking why mount above a drop ceiling, and it's mainly just to do with aesthetics. So you don't have this, this big frisbee hanging from the ceiling with blinking lights and maybe an Ethernet cable sticking out, or you just don't don't want, you know, end users to mess with it either intentionally or to accidentally bump it. So that's why. There's no real technical reason to do it other than maybe the benefits of a little additional height to avoid obstructions between the client device and the access point. Stuart asks, when you mount above the drop ceiling, you mount it facing the same way. So whatever is the bottom, when you mount it on a drop ceiling, it would still be the bottom if you put it above the drop ceiling. So if you're not mounting it to a ceiling or suspending it above the drop ceiling, a lot of people just rest the access point above the on the drop ceiling itself. Mark's got a question here. Can you cluster 2 or more access points on the same SSID so the connection is not lost as the person moves in different directions? Does this involve load balancing? So again, this is, yeah, so generally you want, in a business environment or an environment where it's one network, everyone who's on that one network, every access point should be the same SSID. In theory, the clients are then able to roam between access points as they move around and move closer or further from those access points. Doesn't always work so well in the real world, especially with older devices, but with 802.11k VNR, it makes that go a lot easier. Is there a matrix of all the access points and their specs? There is. If you go to our website, the data sheets generally have all the access points grouped together sort of by the family of access points. But you can reach out to your salesperson and we can send you documentation that's got a feature breakdown of all the APs on a matrix all together in one sheet of paper. Jack is asking, there is a second Ethernet port on many of our access points. Can this be used to cascade access points? So yeah, the access point there is just to make it easier from a wiring perspective. Oftentimes people are adding access points where they've already got Ethernet going down into a wall for a wall plate for a physical connection. So you can use that second port to basically cut the Ethernet there, run one end into the access point, and then run another end out of the access point. So you don't have to you know, string a new piece of cable just for the access point. You can sort of tap in to the existing wire that's already there. You could, in theory, add a second access point to it that way, but there's no PoE pass-through, and most people are using PoE to power their access points. So if you're going to connect the second access point to that Ethernet port, you would need to use AC power to power that access point. Lyle is asking, can we email this presentation? Again, reach out to your salesperson. We can email you the links. Trying to find some questions here. Do you recommend using band steering? And generally the answer to that is yes. Generally you want as many devices on the 5 gigahertz radio as possible. In theory, there's less chance of interference. It's a less crowded environment. There's more bandwidth available, so you can send the same amount of data by using less airtime. So generally you want to try to steer as many clients as possible onto the 5 gigahertz radio. As well as just in general, you want to sort of balance the number of clients connected across each radio. Mark is asking how to detect the hidden node problem. It's hard. It's basically, you'll just see it as a, the easiest way to see it is if you can pull up the specs for the client device or the access point and see the retransmission rate. How many times is it having to resend that packet? If you see it's high, probably hidden node is the cause of that. It's at least one of the main causes of that. Coming out this summer for our big Nebula update, we're adding a report in Nebula that specifically looks at the quality of the wireless connection for the clients. And we'll help summarize that and make it clear which access points are having issues with the RF environment, whether it's hidden node, whether it's co-channel interference, whether it's other stuff, to help you know where those problems are. So that looks like that's it for questions. I don't have any more questions in here. I hope this was beneficial for you guys.